All right, welcome back. So let's get into some actual examples for evaluating the general limit. Now we're going to start with evaluating the general limit from a graph. And when we're doing this, basically what we're trying to do is we're trying to identify the y value that the graph is approaching from the left as well as from the right. And again, we can't do one or the other. It has to be both. And again, the important thing to remember is what is the value we are approaching. The graph does not have to be defined. We're just looking for where are we approaching. And if that value is different from the left and from the right, then we say the limit does not exist. If we are approaching infinity or negative infinity or an asymptote, at this point, we're just going to leave that as a does not exist. We'll talk more about that in later sections of this chapter. All right, so I think on this graph, I have these 6 questions, and then we have 3 over here. So let's go ahead and take a look at here, and let's evaluate the first one. So this one says the limit as x approaches -4 of our function f of x. So this is the function f of x. And we want to say, what is the graph? So basically what this is asking is, what is the graph approaching as x gets closer and closer to -4? So let's go ahead and find -4 on here. And I think I actually have did I do -3? 1, 2, 3. Oh, there's -4. Okay, opposite duh. All right. So here's -4 right here. Now, where's this graph approaching? Now, it's important you can see, like, if you were to kind of think of like a stick figure, right? A stick man, stick woman, whatever, is walking along this graph, right? Jumping up and down, going anything. If they're walking this way from the right to the left, what y value would they be approaching? Like, if you can kind of think of the y values as like maybe like the height or the elevation, you would say, oh, they're approaching 0. And you say, well, what about this person on the left? Like, what are they approaching? Well, the interesting, confusing thing here is they're not approaching anything because there's not even a person there. There's no graph even there, right? This person would fall down, to the hot lava or whatever. So since we're not approaching the same value from the left and from the right, this is actually an example of a limit that does not exist. All right, I don't know why I chose that one first. So let's maybe get into one that's a little bit easier, or a little bit easier to kind of recognize. So the next one says limit as x approaches 2 from f of x. So here's 2, right? So we're saying, all right, as the graph is approaching 2 from the left as well as from the right, what y value is it approaching? Again, think of like the y values as like the elevation on a mountain, right? I don't know. Think of this as like you're on a mountain. This person's walking from the left. This person's walking from the right. What y value, what elevation are they approaching, right? They're both trying to approach 2. What elevation is it? And you can see, oh, that's the value of 4. Now let's do the next one, which is -2. So -2 is over here. Now here it gets interesting because as this person's walking in -2, they're going to go up to what? 1, 2, 3. As this person is getting closer and closer to -2, what are they approaching? They're approaching 1. So from the right, they're approaching 1. From the left, they're approaching 3. Well, that doesn't mean that there is no one exact value, right? So therefore, the limit in that example does not exist. All right, the next one is, what about if we're approaching 3? So let's go ahead and find 3. Here's 3. So as we're approaching 3 from the left as well as from the right, you can see that we're approaching the value 1. So kind of easy. I like that one. What about 0? So 0 is interesting. So here we're approaching 0 from the left and we're approaching 0 from the right. Now, again, it's undefined, but it's very, very important for you to understand this. Even if the graph is undefined, it's what are we approaching? What are we getting really, really close to, right? And you can see that we're getting really, really close to the value of 4 on the graph, right? We're never going to achieve it because it's obviously an open circle, but that's the value we are approaching. That's what the limit is, which we're looking for. All right, and the last one is example number 5. 5. I don't want to go to 5. Why am I going to 5? Let's go to 4. Do I have a? Yeah, let's do 5. I'm sorry, 4. I think I made a mistake there. So in this case, you can see that, oh, these are 2 different values, right? At 4, 2 different values. I didn't have anything defined for 5, so I think I wrote that down wrong. So you can see from the left and from the right, they're approaching 2 different values. So that's does not exist. All right, let's look at the next function, graph g of x. All right, so this one is what is the graph approaching as we're getting closer and closer to negative 3? So we look at this at negative 3, so 1, 2, 3, and you can see this is an asymptote, right? And you can see that from the left, it's going really, really far down, right, to negative infinity, and from the right, we're going really, really far high up to positive infinity. So since we're not approaching an actual finite value, we say that the general limit does not exist. The next example is probably one that's really commonly missed as well, kind of like when we just have an open circle, because this function is actually defined, even though it's at not even though it has an open circle at 0, it's defined up for 0, right? Because there's an open dirt, so it's a discontinuity, it's a hole, but it is defined with this dot. But again, the question is, as we're approaching 0 from the left and from the right, like, where am I squeezing those? Where are those arrows meeting? Those arrows are going to meet at the value of 1, 2, 3, right? The function is defined at 4, but the arrows are going to meet at 3, right? And that's the answer to the question we're looking for. Where is the graph approaching as x is getting closer and closer to 0 from the left as well as from the right? All right, and the last example is 3. And here you can say that, all right, well, they're both approaching, like they're both going up. So they're kind of both approaching the same value. And the tricky thing is, well, they're not really approaching a value, right? They're approaching 1, 2, 3, right? As x is approaching 3, they're going higher and higher, right? So you could say they're approaching infinity. Now, technically, per our definitions, infinity is not a finite number. So technically, we like to say that the general limit does not exist. However, based on your test or whatever, a lot of times if you have the graph is approaching the same area from the left and from the right, we can also define that as like infinity if they're both going up from on there. All right, so that's how you take care of it when you're looking at the limit, the general limit from a graph. What about if we're looking at it algebraically? Now here, what we're simply going to do is we need to understand continuity. And that's why we spent time in that last section understanding continuity, understand what it means for a function to be continuous. Because if a function is continuous, for instance, this graph, 2x plus 5. Well, this is really important to understand what this graph looks like. Because 2x plus 5, it's going to look something like this. I don't care what value I'm trying to approach, right? It's going to be defined. Right? The limit is going to exist. So that's really important. When we have a continuous function, then we know, or if we have a value that's going to be, if we're evaluating the limit on a continuous function, we know that limit is going to exist. So we don't really need to know what the graph is. We don't need to graph this. All we simply need to do, if we want to find the y value, right, where this graph is approaching, all we simply need to do is plug it in. So what we can do is we can say 2 times 3 plus 5. So just substitute in your value that you're trying to see where the graph is approaching and to find that value. And in this case, that is going to equal 11. All right, the next one here is we have the limit as x is approaching 0. Now this one we have an issue because in this case, we can't plug in 0 because you're going to have your denominator is going to be 0, and we can't have our denominator equal to 0. So what I'm going to do is I'm going to simplify this by factoring out an x. Now, when I factor out an x, I recognize, hey, that divides out. That gives me 3 over x minus 1. Now, this is important because this has an asymptote. But one really, really important thing you got to understand, are we trying to evaluate the graph at 1? Right? There's an asymptote. There is a vertical asymptote at x equals 1. But again, look at what the graph is. Besides at x equals 1, we know there's a vertical asymptote. And let me actually just sketch the graph real quick for you. So there's a vertical asymptote here, horizontal asymptote here, and the graph is vertically stretched there. But whatever, it's going to look something like this, right? Okay. The important thing that I want you to realize, though, is this graph is discontinuous at 1, right? There's a vertical asymptote. But all other values of this graph is defined. It's defined on its domain. That's really important to understand because we're not trying to evaluate the limit. We're not trying to understand where is the graph approaching at 1. We know there's a vertical asymptote there. We know that limit would not exist. We're trying to find where is the graph approaching at 0. Well, since 0 is not a discontinuity, I can just plug that in. So that's exactly what I'm going to do. And therefore I get a negative 3. Right? Because that's what we're looking for, that value right there. So just be careful because a lot of times when we deal with discontinuities, students will get stuck with, oh, it's an asymptote. Oh, it's a hole. That must be where it's going to be. And that's not always the case. All right, the next example is a square root function. And again, this one's really important to understand what this graph was going to look like. So let's go ahead and just do a quick little sketch, because you can easily plug in 3, right? A lot of students will go, so, oh, let's, if I just plug in 3, like we're good to go, right? Square root of 0, that's just going to equal 0, done. But that's not the answer. And the reason why is because the shape of the square root function. So this is being shifted 3 units to the right, 1, 2, 3. It's going to be reflected about the x-axis, and it has a vertical stretch. And what I want you to see is, we're trying to evaluate it at 3. That's an endpoint. The limit for the limit to be true, we have to approach from the left and from the right. So for it to be defined, it has to be approached from the left and from the right. And you can see that we can approach 3 from the right, but we cannot approach it from the left because there is no graph from the left, right? I can't put a stick man on any graph over here. There is no graph that exists. So therefore, this is an example of does not exist. All right, the next example. So we have a rational function. A lot of times I'm like, oh, rational functions, let's factor. All right, so I see a perfect square trinomial, but I'll just leave it like that. And then I see an x minus 3 times a x minus 1. All right, so my x minus 1's divide out, right? So that's going to be x minus 1 all over x minus 3. Okay, now x minus 3 does not divide out. Now, what that tells me is that's going to be an asymptote, right? I know there's a vertical asymptote that is going to exist right there. So therefore, in that case, without going into further details of what this graph looks like, we can just leave it right now, in this case, for the being a does not exist. Now, if you want to know what actually the graph looks like, just in case it is approaching something, what you could do is you could do long division to be able to rewrite this as a reciprocal function. So if you just remember, we can just take x minus 3 and divide that into x minus 1. So x goes into x 1 times x is x, 1 times negative 3 is a negative 3. Subtract your rows. That's going to give me a 0, and negative 1 minus negative 3, that's going to be 2. X does not go into 2, so that's my remainder. So that's going to be plus my remainder over my divisor. So therefore, this technically is in the form of 2 over x minus 3 plus 1. Now, if you know what that graph looks like, you could see that this graph, right, is going to be shifted 3 units to the right and shifted up 1. So there's a horizontal asymptote there, and the graph is going to look like the reciprocal function. So I'll just graph it like, something like there. But either way, you can see that, yep, that's the reciprocal function. It does not exist. Okay, so obviously if you have graphing technology, you could do that quicker, but it's important to know how to rewrite a rational function if you, in its reciprocal form, if it is able to do that. So therefore you can understand the graph. But again, when you have an asymptote, it's not approaching any value. So therefore, in this scenario, in this case, we can just do does not exist. All right, in the next one, we have piecewise function. Now we have to go back again to our chapter 1 and really make sure we remember how to graph piecewise functions. So again, what we're going to do is we're going to graph these separately based on their restrictions. So what we have here is we have the V-shaped graph and a linear graph. So for the V-shaped graph, that's going to be shifted over 2 units. All right, and let's give me, so this is only going to be x is greater than 0. So again, that's going to be, if you remember, over 1, up 1, over 1, up 1, over 2, up 2. But again, it's open circle, and then over 2. So this graph's going to look something like this. No, I don't want that. Let's do it again. Cool. All right, that's what that graph looks like. And then this is going to be a linear equation. So that has a y-intercept of 2 and a negative slope of 1 to 1. So it actually looks something like that. So it actually continues the graph. Kind of cool. So again, where are we approaching from the left and from the right? What value are we approaching? And you can see the value that we are approaching is 2. So this limit, a lot of times we'll use this as a value, if we call this like f of x. So we could say the limit of as x approaches 0 of f of x is equal to 2. All right, let's look at this next one. So again, this next one is, let's go ahead and graph it. So I have negative 2x, which again is going to be a linear function with a y-intercept at 0. So negative 2, 1. That's a less than or equal to. So it looks something like that. Awesome. And then we have 2x squared plus 1. So that's going to be up 1. And then I'm not really sure, 2x squared plus 1, that's going to be an open circle. Should have done a little bit higher. and then that's going to be a quadratic. So it's going to look like there. Now, again, you can see that these y-intercepts here are different, right? From the left, it's going to 0. From the right, it's going to 1. So let's call this g of x. And we could say limit as x approaches 0 of the function g of x. That is does not exist. Because you can see we're approaching two different values from the left and from the right. All right, ladies and gentlemen, that is it for your examples in the general limit. Go ahead and give the quiz a shot, and I look forward to seeing you in the next video. Cheers.